Right, welcome back everybody. So this afternoon we're going to look at some of the features that have been more recently added to OpenMP. Well, some of them aren't that new now. We'll start off with a collection of things that you might not be, that don't get used so much or you might not be so familiar with. And then I'll finish up with talking about the GPU offloading features, because that's kind of the main big change that's happened to OpenMP in the last few years. Okay, so start off just a little bit of history. So yeah, I mean, it was almost 10 years ago since the offloading was originally added into OpenMP. It's taken a while to get into decent implementations, and it's also evolved somewhat as well. So some of the early design decisions weren't quite right, and things have been fixed and added since then. So depending on which compiler you're working with, you're probably likely to see, so most compilers support 4.5 or 5.0 these days. We are up to 5.2 now, but the 5.1 and 5.2 are mostly fairly minor changes, and they're not yet in most production compilers. Maybe the biggest change, so thing to point out, version 5 essentially basically updated the versions of the base languages. So it did a lot of work to to support more modern versions of C, C++, and Fortran as the base languages. Because prior to that, the base language support was kind of for only for what were really quite old versions of the base languages. What I'm going to cover here, I'm going to talk about user-defined reductions, construct cancellation, Simile directives, some more bits and pieces with tasking, and thread affinity. Okay, so let's start off with user-defined reductions. Okay, so prior to 4.0, you were not able to do reductions on objects or structures. You're only able to use essentially basic types or arrays of basic types in reductions. But the more recent support allows you to declare your own reduction operators. And so you do this with a declare reduction directive that defines the operator, and then you can use those in the normal kind of way in reduction clauses on parallel regions or parallel loops, for example. Okay, so syntax for this looks like OMP declare reduction, and then we find a pointer here, then we give it a reduction. So the reduction identifier just gives it a name, so that we can refer to it. So it gives the operator a name, which we can then use in the reduction clause. A list of types to which it applies, and then basically a code fragment that describes how to combine two elements of these types, because that's all you need in order to be able to build a reduction. Just need to know how to combine two elements, and then you can sort of concatenate that and reduce as many as you like. And then optionally, you can also specify the identity expression for the. you can give the identity element for the type. Okay, so that's the value to which the private copies are going to get initialized at the start of the parallel construct. Okay, I think I've got ahead of myself and said all that. Yeah, so the identifier can be overloaded for different types. So if you want to reuse plus operator, for example, for you want to define a plus operator for some object, then you can do that. Okay, so here's an example. So suppose we want to define a reduction operator that merges vectors together. Okay, so it just concatenates vectors into one long vector. So we could use declare reduction here. We give it a name, call it merge. Give it, so what type does it operate on? Okay, it operates on the stud vector class specialized to ints. And then we give this basically expression which it says how to merge two vectors together. Okay, so there are two special defined variables. There's omp out and omp in. So one of those, so omp out refers to the private copy that's going to hold the combined values. Okay, so we're going to combine omp out and omp in and produce omp out, overwrite omp out. So basically, so for merging, what we want to do is in omp out, we want to insert at the end of omp out the elements from the beginning of omp in to the end of omp in. Basically, so this is just the standard methods on vector class to do this. Okay. So now that we've defined that, we can then use merge as a reduction operator. So we can have a reduction clause that says merge colon and then a vector, and that will work. So this is so probably most useful for C++ programmers who want to be able to define reductions on objects. Next one is construct cancellation. So this is a clean way to signal early termination of an OpenMP construct. So if you want, at some point, you've got multiple threads executing inside a parallel region or parallel loop, and you want that situation where some event happens in one thread, and you want that thread to be able to signal all the other threads and tell them to jump to the end of the parallel construct. So it's not what they're doing, and go to the end of the parallel construct. So it's kind of can be quite awkward to do. You can code it yourself, but it's kind of messy. So this is a convenient way of doing that. So the idea here is that one thread is going to raise a signal at some point, and then as soon as the other threads observe that signal, okay, and there's various points in the program in which they're going to look for it, then when the other threads observe the signal being raised, they will jump to the end of jump out of what they're doing and go to the end of the construct. So the way this works is there's a cancel directive. There's OMP cancel. Okay, I have to tell it which construct where we want to jump to the end of. So that could be parallel or sections or do or for in C++ or task group. And then there's also this can be done there could be a condition attached to this as well. Okay, so the cancellation will happen if the expression here evaluates to true. Then you can also specify a cancellation point. So that is a point at which threads will check to see if the signal has been raised. So that also happens implicitly at the cancel directive. Okay, so the cancel directive itself is also a cancellation point where it checks for other threads and also other places as well. So typically barriers, for example. Whenever you get to a barrier, then the threads will also check for the signal. So you can do something like this. So suppose you have a parallel loop and you're searching for something. So you want as soon as something has been as soon as you found the thing, or one of the threads has found the thing in one of the loop iterations, you want to stop and want all the threads just to jump out in the end of the loop. So you could do something like this. Okay. So you could have your parallel loop, and basically for every value of I, you do some test, and okay, you set a flag to say whether the test was successful or not. And then if the test was successful, so you found something, then you can say, okay, cancel parallel region at this point. And so the first thread for which Eureka is true will cancel the parallel region. All the other threads, the next time they encounter this cancel directive, that also acts as a cancellation point. So they will observe the signal and jump out the next time they get to the end of an iteration of the loop. It's kind of an alternative to support a break inside an OpenMP parallel region. Yes, but it's obviously it's kind of a bit more useful if you have so you can have the cancel can be inside anywhere down inside the call tree. So you might want to do the break somewhere in 3 levels deeper function calls, and this allows you to do that without modifying the whole call tree and propagating the break back up your call tree and checking at every level and that kind of thing. Yeah. So it basically says, yeah, it allows you to do a break and inside a parallel loop. Okay. So the next one is the portable SIMD directives. So this one's a little bit strange because at first sight, this has not very much to do with the rest of OpenMP. This is supporting basically vectorization optimization in the compiler. So the problem is that most compilers supported something, but they supported their own directives to do this, and it wasn't standardized across different compilers. And rather than invent a completely new standard, it was kind of thought, well, OpenMP OpenMP standard is a reasonable place to put this stuff, and because it's more or less orthogonal to the rest of OpenMP. In some sense, but it reuses some of the concepts, so it's not a crazy thing to do. And so now have a standard set of SIMD directives in OpenMP. So basic directive is the SIMD directive to indicate that a loop should be SIMDized or vectorized. So it says. So this says, please execute the iterations of the following loop in SIMD chunks. So basically generate the instructions that do vectorization multiple iterations at a time. So the Simile directive itself does not divide the loop across threads, it just does the vectorization. So if you want both, you can use a combined directive. You can do OMP for Simile on the loop, and that will both parallelize across threads and vectorize. So there's various clauses that apply from this. You can say, okay, safe length puts an upper limit on the number of iterations in a chunk. Linear is basically deals with variables with a linear relationship to the iteration space. So that is where you have, or otherwise called induction variables. Okay, so if you have a variable that's incremented by a constant amount on every iteration, then formally the compiler will look at that and say, oh, well, that's a dependency between iterations, because I need to know the value from the previous iteration for the current iteration. So you can say, okay, these variables behave like that. So the compiler can do a transformation and calculate them directly as a function of the loop iterator rather than incrementing them. Probably the most important one is the aligned one, because this is the information that the compiler is often lacking to be able to safely generate vectorized code. So you can specify the byte alignments of variables. So most Simile instructions operate on several words of data, but they usually require that the first element of the vector is aligned to some byte boundary. It's aligned to say a 32 or 64 byte boundary in memory. And in general, the compiler can't always tell what the alignment is of variables, particularly if they're passed by address through an argument list. Then the compiler essentially has no knowledge of the alignment. So this allows you to tell the compiler what the byte alignment is, and help it generate the vectorized code. So you can also have private and last private and reduction and collapse clauses, which have the same meanings as they do for parallel loops. And there's also a declare Simile directive, which will generate vectorized versions of function calls as well. Okay, so that some restrictions, obviously, they have to be basically pure functions. Yeah, you can do that, and then you can combine this with the loop constructs to do both thread parallelization and vectorization on the same loop. Okay. Next one is some extra stuff with tasking, some extra extensions. Okay, so task loop is just a convenience as a way of turning a way of generating tasks straightforwardly from loops, to turn loop iterations into actual OpenMP tasks. So you can obviously always rewrite that. You can basically block your loop and say, okay, this group of iterations and do it with explicit task constructs. But it's slightly messy, and it's something that the compiler can easily do. So let's have this task loop construct. So what that does is it basically takes chunks of loop iterations and turns them into OpenMP tasks. And that's what this grain size parameter does here. That says how many loop iterations should comprise a task. You can also do it the other way around. You can also specify, instead of specifying the grain size, you can also alternatively specify the number of tasks. So how many tasks you want your loop divided into, and then it'll figure out the grain size from that. And then there's also task dependencies. So this allows you to specify ordering constraints between tasks. So normally when we generate normal tasks, we're basically saying that the tasks can be executed in any order. But that's not always true. So there are cases where you want to be able to specify some orderings between tasks, and there are cases where using task weight isn't convenient or isn't the right thing. So you can do that with these with this depend clause. So the depend clause takes a dependency type colon a list of variables. So the type can be in, out, or in, out, and the list is allowed to contain subarrays. So OpenMP includes a syntax for subarrays in C and C++. So this can also be used to specify reductions on parts of arrays and other things. So there's a few other places where the ability to specify subarrays is useful. So the problem with, for example, doing reductions on arrays in C++ is, in general, all the compiler sees is a pointer to the start of the array. It has no idea how big it is. So the subarray syntax gives us as programmers a way of telling the compiler how big the array is, and therefore how big the private copies for the reduction should be. So that syntax has other uses as well. And okay, so basically it says so. This is essentially doing dependencies based on the address of these variables. Okay? And it basically says that, okay, so if I have an independency, okay, that means that this task will be dependent on all previously generated tasks, and they have to be sibling tasks. Okay, so that means it only works. This only works at with ones at the same level of nesting. Yes, Vlad. Sorry. So I'm showing a mixture of C and Fortran here. All this stuff has equivalents in both base and all the base languages. Yeah.
No insult. Yeah, thank you.
Yeah. So, yeah. Okay. So instead, yes, this only works for this. You can only specify dependencies between tasks at the same level of nesting. You can't do dependencies between tasks at different levels of nesting. So this says, okay, so if it's an independency, then this task depends on all previous tasks that reference at least one of those variables in an out or an in-out clause. And actually, out and in-out are semantically the same, okay? So it's just slightly confusing. So in-out is just meant to be in and out, but in fact the behavior is just the same as out. So it says, the generated task will be dependent on anything that references at least one of the items in any depend clause. So this looks a bit weird, but it basically says, okay, it's basically dealing with anti-dependencies. Okay, so if two tasks write to a variable, to the same variable, you can specify that the first task that writes to it must happen before the second one. So a very simple example, you can do things like this. So I can have say a task that has an out dependency on A, second task has an out dependency on B, and then a third task that has an independency on both A and B. So that would mean that these first two tasks can execute in parallel, but the third task has to wait until the first two are finished before it executes. So that's just a very simple example of how this works, but you can get quite sophisticated, and it's actually possible to implement entire algorithms with nothing else but tasks and dependencies, and it's quite an interesting but very different way of doing parallel programming. So it's basically data flow. You're basically able to do data flow style programming in OpenMP these days, which is, say, it's not what you want to do all the time, but there are some applications where this is useful. So it's possibly the main area where it's used and very successful is for some dense linear algebra applications where you have several different functions going on with quite complicated dependencies between them in these linear algebra algorithms, and you can you don't always know it's difficult to know the relative execution time of the different parts of the algorithm. So it's difficult to specify a fixed order in which to do things in. So using tasks with dependencies means that you're basically saying, okay, these are just the orderings that need to be respected, but you can execute stuff as soon as its predecessor tasks are ready. You can execute anything that's available to be executed. So you can get some quite nice performance gains from doing some of these things with tasks and dependencies. Okay, and lastly is thread affinity. So this is binding. This is about binding threads to hardware entities. So they have some more control available. Okay, Lorenzo says, suggested yesterday GPU streams and events sort of maps into tasks and dependencies. Yeah, it's kind of a similar idea. You're identifying tasks and separate pieces of computation and specifying some ordering between them. Yeah, so there's definitely a reasonable analogy there. Yeah. Good. Yes. So now we have these really complex hierarchical hardware designs. So NUMA regions, hardware threads, shared caches. Then clearly placement of threads on the hardware can have a substantial effect on performance. So what OpenMP supports is actually increased number of choices for the OMP proc bind environment variable. So you can still specify true or false. So true says just bind my threads, but it doesn't tell the runtime how to do it. It says, please bind my threads to cores, but it doesn't say which thread goes to which core. And so it can now provide a list with possible values of master, close, and spread, which specify how to bind the parallel regions at different levels of nesting. And there's also an OMP places environment variable. So this can either contain abstract names, so that can be threads, which in this case means hardware threads, or cores or sockets, or you can specify an explicit ordered list of places. Okay, so you can give a list of core numbers, for example. The actual way the numbering maps onto the hardware is still implementation defined. So this is kind of semi-portable. It's a portable mechanism, but you still have to know, or you may still need to know exactly how the hardware numbers its entities, and that's kind of it's basically an OpenMP runtime and operating system dependent thing. Okay, so you can do things like this. I think this example looks actually wrong to me. Oh dear. Okay, so suppose you have two levels of nested parallel region. Okay, and you have your hardware has 8 cores and 4 hardware threads per core. Okay, and I have 2 levels of nested parallelism. So so this is what's wrong here. This should say OMP num threads equals 4, 4. Okay, so I have 4 threads for the outer parallel region, and then 4 threads for each of the inner parallel region as well. And so then I can specify that OMP places is the entity, the binding entity I'm talking about is hardware threads, and the binding pattern that I want is spread at the outer level and close at the inner level. Okay, so these things have specific meanings. There's a whole section in the OpenMP specification which basically gives which specifies the algorithm for determining what happens here. Essentially, what will happen is that, okay, so the original master thread is going to run on. So here we've got our 8 cores are the blue squares, and then each of the white dots here represents a hardware thread. We've got 4 hardware threads per core. Okay, so the original master thread, the initial thread, is going to be bound to thread 0 on core 0. And then at the top level, the threads are going to be spread out as far as possible. So they are going to be, they're going to get spread out as far as they can, equally spaced across the threads and cores. And then at the bottom level, so the actual meaning of close here will actually result in this pattern. So if when this thread spawns its inner parallel region of 4 threads, they will get bound to 2 of the cores on 2 of the threads on this core and 2 of the threads on this core. So you can, it allows you to arrange it's a little bit complicated and messy, but it does give you a mechanism for arranging different patterns of binding of threads to cores. As I said before, with batch systems, then mostly you don't need this stuff. It's mostly taken care of by the the bindings mostly taken care of by the batch system rather than the OpenMP runtime. So Lorenzo says this cannot be done at runtime. Well, you can't do it inside your program. So saying this is all you set your environment variables before you run the program, but you can't change stuff inside the. I don't think you can change stuff once you're inside the program. I would need to check that. A possible solution for NUMA woes. Well, yes, but this just tells you where to bind your threads. It doesn't say anything. You're still subject to, you still have to worry about where your data is going to get located. So this just allows you to place the threads in the hardware. But that doesn't necessarily determine where your data is going to go. But for example, if you wanted to try and solve your NUMA problems via nested parallelism, then yes, then at least you have the power to get the binding right. Mostly with batch systems, it's done through the batch system, but you'll occasionally see systems where you maybe you need to do a bit of both. Okay, seen at least one batch system where you need to say, as well as you need to specify OMP places equals cores to make sure that that it actually binds, that it basically doesn't use hyperthreads. You tell it to put OpenMP threads on different cores in preference to that's not the default. Yeah. It very much depends how your batch system is being configured. Okay. Yeah. You can get some nasty. You say it's all depending on how exactly the configuration, and there's myriad ways to configure batch systems like Slurm, and what it does by default is not necessarily what you want. Kevin says, yeah, there's a proc bind clause on parallel regions. Okay, yeah, so maybe you can do that rings a bell. So yeah, you can do something at runtime. So you can maybe allows you to bind change the binding for individual parallel regions. Thanks, Kevin. Okay, any other questions on this one? Okay. Let's move on to talk about the Accelerator offloading stuff then. Okay. So this is a fairly high-level view, or a fairly introductory view. I say could run a whole day, at least a whole day's course to go into more detail. But it's intended to give you sufficient flavour and a sufficient introduction that would get you going with this if you were keen to try it. So unfortunately, we don't have any. So ARCHER2 does not have any GPU nodes that we can try stuff on. So the accelerator support in OpenMP is the way it's been designed is that it isn't completely bound to GPUs. So it's designed to be not completely GPU specific. However, there's not really many other interesting devices around at the moment. When the accelerator support first came out, it was also designed to work, and there was an implementation for Intel Xeon Phis, until Intel decided that, well, first of all, they didn't want to use Xeon Phis as accelerators anyway, and then finally that the Xeon Phis were they canned the product. So at one time it did work on Xeon Phis as well. There's also an implementation for Texas Instruments have an implementation for their DSP chips. But say apart from that, most of the implementations are for the interesting implementations are all for GPUs. So it's kind of fully integrated into OpenMP for the CPU. So everything is designed to work nicely together. So it was originally came in version 4.0, but there have been significant revisions and extensions to it in 4.5 and 5.0. So in many ways, it's similar to, but not the same as the OpenACC set of directives. So OpenACC is an alternative standard for offloading GPUs, which was developed before OpenMP 4.0. And it was essentially a bunch of companies who got bored waiting for OpenMP to standardize something. So they went off and did their own thing. Kind of with the sort of original hope or vague intention that it would eventually make its way into OpenMP, but OpenMP decided to do something different. I say partly because OpenACC is very GPU specific, and the politics in OpenMP at the time dictated that wasn't really acceptable. So anyway, we've ended up with essentially two ways of offloading to GPUs using directives. The functionality in the two is pretty much equivalent. So anything you can do in OpenACC, you can do at least in OpenMP 5.0, and vice versa. So the syntax is all different. Some of the details are different, but the functionality is pretty much equivalent. So anything you can do in one, you can do in the other. There are now more compilers supporting OpenMP offloading than there are supporting OpenACC. But some of the OpenACC ones have been around for longer, so they are perhaps better optimized. So yeah, you take your choice. Okay, so OpenMP is probably portable across more different platforms, but may not be, on some. On particular for NVIDIA GPUs, then OpenACC may still perform better. Okay, but so a bunch of different compilers do support this for various different bits of hardware. So Cray, NVIDIA, IBM, LLVM, Clang, GCC all have offloading implementations for at least some hardware. So the way this works in OpenMP needs quite a substantial change to the execution model to be able to cope with the fact that now we don't have just a single shared address space. We've got a host and devices that have separate memory spaces. So it's the OpenMP model is a host-centric model. It assumes you have one host device. So in other words, your CPU processor and multiple target devices. So you can have it can support more than one GPU attached to your host, but it kind of assumes that they're all the same. Okay, so you can't have. It doesn't support a heterogeneous mix of offload devices. So a device is defined as some logical execution engine with some local storage. And then there's a data environment. A device data environment is a data environment associated with one of these target data or target region constructs. So there's basically this is the OpenMP's way of coping with the fact that there are separate address spaces, separate memory spaces in the hardware. So there are a set of constructs. They all start with target that control how both data and code is offloaded to a device. And the way it works is that data is mapped from the host data environment to a device data environment. So the variables have the same name on both the host and on the device, but there are, then the appropriate copies are made at various places to map the host copy to the device copy and back again. So in the same way that the parallel region is the basic parallel construct in OpenMP, the target region is the basic offloading construct in OpenMP. So like a parallel region, it defines a section of the program. And the model is, so kind of the analogy to the parallel region is that the OpenMP program starts executing on the host. When a target region is encountered, the code it contains will be executed on the device. Okay? And by default, if we don't specify anything else, the code inside the target region will execute sequentially on the device. So the target region, the target construct of itself does not specify how the code gets on the device gets parallelized. So we need to do extra stuff for that. At the end of the target region, the host and the device synchronize. So the host thread waits for the target region to finish and then carries on executing the next statement. Okay? So there is a way to talk about that. There is a way to get rid of that synchronization if you want to, but by default, it's basically a blocking offload. The host will wait until the target region is completed. So it just looks like OMP target with a structured block and the usual equivalent for Fortran. So the model looks like this. So you basically start executing on the host. It's a sequential part of the OpenMP program. And then you get to a target construct then the code inside the target construct. Let's give it a pointer. The target inside the code inside the target construct gets offloaded onto the device. In the meantime, the host will wait. When the target construct finishes, then the host carries on executing again, and so on. So that's kind of the sort of analogous picture to parallel regions. Okay, so yeah, so we need to deal with different copies of our data. So the host and the device have separate memory spaces, but they refer to variables by the same name. So in order to access the data inside the target region, it has to have been mapped to the device. So which will cause a copy to be made. So the map data, so while the device is using it, that map data can't be accessed by the host, okay, until the target region has completed. So there's basically says, you know, it bans you from having, OpenMP bans you from having races between the, you know, having the host and the device access the same variables at the same time. So there's never any, you know, there's never any conflicts to resolve. So the default behavior is changed depending on which version of OpenMP, but basically scalars that are referenced in the target construct are treated like first private variables. So you get a new copy on the device, which is initialized with the value on the host. Static arrays are by default copied onto the device on entry and back to the host on exit from the target region. But for other things, we normally need to take control via the map clause on the target construct, which specifies how the copies are, which variables need to be copied and in which direction. Okay, so it looks like OMP target map, and then a map type colon list of variables. So the map type can be to, so that means copy the data from the host to the device at the start of the target region. So from says copy the data back to the host on exit. So as you might expect, to from does both. Okay, so copy data to the device on entry and back again on exit. But you can also just have alloc as well. So this just says, okay, I don't actually need to copy any values. I just want to scratch. I just want to scratch copy on the device. So this will allocate an uninitialized copy of those variables on the device and doesn't actually copy. It actually doesn't copy any of the values. Okay, so a very simple example would be, okay, so for a loop like this, so you could offload a loop like this with a target, and you would want to specify the mapping. If you want to specify it explicitly, then you'd say, okay, so these arrays B and C are being read. So they need to be mapped to the device, but they're not being modified, so they don't need to come back again. Whereas for sum here, so we need the initial value of sum to be copied onto the device, and we want the final value to be copied back again. So you would use map to from for sum here. So this server itself, So is this supposed to allocating only on the device? Basically, so we mean different from alloc? Yeah. So you only ever have a copy. Yeah. So alloc without any host mapping. Oh, good question. I think there is, but I can't remember how you do it off the top of my head. I think if you do alloc here, there has to be a copy on the host in order for it to know what to allocate on the device. Yeah. But I'm pretty sure there is a way just to allocate stuff on the device if you want. So yeah, I'm gonna have to go away and look this up as to how it works these days. So it's just one of these things that's changed in recent recent versions of OpenMP. Okay, so for dynamically allocated data, then again, it's like it's basically like we've seen before. We need to use this subarray syntax in order to specify the number of elements to be copied. Okay, so if we malloc some data on the host and we want that mapped, we have to specify the basically the starting element and the number of elements that get mapped using this this square brackets syntax. Okay, but you can also use that to specify part of an array. So it doesn't have to start at 0. You can specify a contiguous part of the array. Does it work the same for objects or containers? There are ways to do it, but you basically have to write specific mapping functions for your objects. So you have to implement basically a mapper so that it can figure out how to do the mapping. There are ways to do it. Yeah, so 10:3 means 10, 11, and 12. Yeah. So this is kind of annoying, okay? Especially if you come from if you're used to Fortran subarrays. And so basically in C++, the syntax is start:\length. So whereas Fortran subarrays are start:\end. So yeah, they had their reasons, I guess. Okay, so keeping data on the device is important because on current hardware, moving data between the host and device is really expensive. So we'd like to avoid, if we don't want to have to map data for every target region, if we can if we're able to keep it on the device between target regions. So there's other constructs. So there's target data construct, which just maps the data and doesn't offload any code. And then there's target update, so that you can at any point you can do copies back and forth between the host and device without offloading any code. So you can do things like this. You can do OMP target enter data. So at this point in the program, you could map these arrays A and B to the device. And then you could have a whole series of target regions, offloaded code sections, which access A and B. And maybe you're doing something on the host in between. So that so that it's not possible to wrap this up into a single target. And then once you're done, then you can map. Say you can get, maybe you only need B back again at this point. You can get B back from the device. So it allows you to decouple the data copying from the actual code offloading. And then be using for updates, for example. Okay, so you might also so map variables devices simply copies. Yeah, so changes within the target region won't change their original on the host and without using from. Yeah, that's absolutely right. Yeah, yeah, yeah. So target update allows you to do copies either direction at either time of parts of your data. So again, you might say, okay, at the beginning here, I want to map the whole of A and B onto the device. Then I have a region that does some computing with A and B, and then at this point, I just want to get, say, the first element of array A back to the host. So I can do an update from. Then I can modify A0 on the host, and then push the new value back to the device with an update 2, and then carry on doing more things like that. Okay. So it allows you to basically do copying of partial copies or full copies of data items back and forth between target regions at any point that you feel like. Okay, so that's a sort of rough outline of how all the data copying works. But now we have to think about, okay, so what about parallelism on the device? Okay. Well, in principle, we can use all the normal OpenMP constructs inside a target region to create and use threads on the device. So parallel regions, work sharing, all the synchronization, tasks, etc., etc. But GPU hardware doesn't support a full threading model outside of a single stream multiprocessor. Okay, so where GPUs are built, they have lots of these single stream multiprocessors, each one of which can run, each one of which has multiple cores running multiple threads. So basically, you don't have any, or you have very limited ability to synchronize between stream multiprocessors. They have their own level 1 caches, but they're typically not kept coherent. So that means that a parallel region inside a target region can only execute on one of these SMs. Okay. So basically, this is, if you're familiar with the CUDA, this is the same idea that you can really only synchronize threads inside a thread block and not between thread blocks. So how does this work on an OpenMP? Okay, so yeah, so for this example here, if I just had a parallel 4 inside my target region, then on a GPU, so some other device that might work fine, that might be all you need, but for a GPU, that's only going to use one stream multiprocessor, which is probably not much use. So for GPUs, we need something extra. And this is the way this works in OpenMP is through the teams construct. So this basically essentially creates multiple master threads inside a target region. And then each of those master threads can spawn its own team of threads with a standard parallel construct. But the restriction here is that threads in different teams can't synchronize with each other. So synchronization constructs like barriers, critical regions, locks, atomics, they only function between the threads in a team and not across different teams. So you have some control here. You can set the number of teams you want created. You can get the team ID and the number of teams that are executing, for example. So it's a bit like MPI communicators. Yeah, kind of, yes. Okay. So basically, yeah. So it kind of looks like this. So when we offload, basically you can do a target region which contains a team construct, which then also contains a parallel construct. So the target does the offloading. The teams construct creates these multiple master threads. And then in turn, each of those master threads creates a separate, okay, each of those teams can then fork threads in a parallel region. So that's how you get this hierarchical parallelism that maps onto the GPU hardware in OpenMP. But there is this basically restriction that yeah, so team is basically the same as a thread block here. Yeah, that's the analogy, or at least the mapping to the hardware is the same. Yeah. Yes, it's one-dimensional. Okay, if we have more than one device, then we can specify the device number on the target, basically on the target construct. So you can explicitly offload to different devices. So OpenMP has mapping comes first before the teams. Teams share, yeah. Okay, so all the teams see the same shared copy of data on the device. Yeah. because OpenMP likes to support loop parallelism really well. So there's also a mechanism for scheduling loops across teams. Okay, so yeah, so if we just want to offload a parallel loop, we'd like to distribute the iterations loop across the teams as well as across the threads within the team. So there's a construct for doing this. Okay, so distribute construct is basically like the for construct, but it assigns iterations of the loop to different teams. Okay, and it also has a schedule clause, but it can only be static with a chunk size. So because of the restrictions on synchronizing, it means that you can't do dynamic scheduling of loop iterations across teams. So it's kind of what you expect. Okay. So if for the full works, what for an example, for a simple example, if you want to use the whole GPU, then you would need to specify OMP target teams distribute parallel for. Okay, so that will basically offload, create some teams, distribute the loop iteration between teams. Each team creates multiple threads, and then also distributes the iterations across the threads. So it's a bit of a mouthful, or a bit of a long bit of typing to do to get everything. Other things, yeah, if you're going to call functions inside target regions, then you have to mark those up with declare target, so that the compiler will compile a version of those for the device for you. Okay. Yeah, okay, so this is how we do multiple devices. There's a device clause which basically says which device to offload to, if there's more than one. So, just takes an integer parameter. Device numbering is implementation dependent, but I guess they all start at 0 and go up in ones usually. Okay, but yeah, you have to figure out what the device numbering. I guess in principle you need to figure out what the device numbering is on your hardware. Okay. As I said before, by default, the host thread is going to, it will block until the target region is completed. You can change that behavior by putting a no wait clause on the target, in which case the host will do the offload and then carry on executing. So actually what happens in that case is that the target region behaves like a task. So you can use task synchronization constructs like task wait, can be used to wait for completion. But in that case, yeah, then you really do need to make sure that the host doesn't access any of the mapped data until the target region completes. Okay. So performance issues are the typical things with GPUs. Transferring data between host and device is very expensive. You need to minimize that as much as possible. So don't transfer anything you don't need, and keep the data on the device as far as possible. So that's same advice as for programming GPUs using any other API. Also, GPUs need a lot of threads to work efficiently. So for your CPU, you need a few threads or a few tens of threads. Your GPU needs you need to be able to expose hundreds or maybe even thousands of threads worth. So you need to expose a lot of parallelism. So particularly, for example, for nested loops, using the collapse clause to parallelize 2 or more loops is a really useful concept on GPUs. And then you also have to, care about the memory layout. Because what works well is different for CPUs and GPUs. For CPUs, having different threads accessing neighboring words in memory is generally a bad thing, because you have this risk of false sharing. I mean, it's okay if it's just reads, but interleaved writes are bad on CPUs. On the other hand, GPUs having threads accessing neighboring words in memory, different threads accessing neighboring words in memory, could be good, because it allows the GPU to generate these coalesced loads and stores. So it depends what you're doing, but if data structures are used on both, then you might need to explicitly change the layout, so to transpose multi-dimensional arrays before you map them onto the GPU. Might also be possible to interchange loops, or say use a static 1 schedule. And in fact, some implementations will actually do static 1 as the default schedule for this reason. Okay. So that's kind of a bit of a quick overview of how the offloading works. Any questions? Looks a bit messy. Yeah, it is a little bit messy, but yeah, I guess, yeah, the potential benefit is portability. I mean, it's until recently nobody cared, because all anybody had was NVIDIA GPUs, but that's increasingly no longer the case. So I think the ability for the portability might be good. Of course, whether you get portability of performance is another matter. But at least you have code that's going to run on different types of GPU hardware. OpenMP stay as a major GPU porting method. Comparison with OpenACC. Well, that's a good question. I don't really have a good answer for that. My feeling is that OpenMP is OpenMP is gaining more use because there are more implementations of it these days. But there's still, there are existing OpenACC implementations around, and they will probably not change. They will probably not go over. So yeah, it's a little bit of a tricky decision as to which you're going to want to use. Say if you use OpenACC, you might get some good performance for NVIDIA devices, but you might also find that although it's in principle portable, you're locking yourself into you're locking yourself into single vendor or fewer available compilers. So yeah, the answer is I don't really know, and these things are very hard to predict as to which way the majority of applications are going to go. Support for numerical libraries. Okay, so you can still use you can still use, there are, OpenMP is still compatible with using these CUDA FFT library, the hardware provided libraries like QBLAS and so on. It is interoperable with those things. So I think OpenMP can handle, you can, OpenMP will deal with, you can use device pointers and stuff like that. So if there is a certain amount of interoperability with CUDA, for example. So if you get a pointer to, you can pass around pointers between CUDA library calls and OpenMP target, for example. So yeah. Matt, I don't know off the top of my head what the default behavior is. As I say, some of these things keep changing between versions of OpenMP as well. So I would need to go and read the spec. You'd also have to read the right version of the spec compared with what your implementation supports as well, I think. Yeah, things like that. Okay, so we'll take a break there. Say, if you've had enough, then please feel free not to hang around. But Kevin and I will be here between 4 and 5 UK time if anybody has any more questions or wants any more help with the practical exercises. That's the last of the lecture sessions.